Hello, today we start our conversation about two beautiful applications of trigonometry to geometry, their laws of sines and laws of cosines. So let's make some preliminary comments and discuss our notation. We will be talking about oblique triangles, triangles that are not right. Let me make a picture of one. We will commonly denote the vertices of this triangle as ABC. It doesn't matter, of course, in which order. Angles will be denoted just by A, B, and C, just like vertices. The length of the sides will be BC, which is opposite angle A, will have length A, lowercase a. AB, which is opposite angle C, will have length lowercase c. And AC, which is opposite angle B, will have length lowercase b. Before we formulate the law of sines, our first major result here, let's discuss two important circles associated with every triangle which is non-degenerate. Non-degenerate means the vertices of the triangle don't lie on the same line. So we exclude a situation like this. So with every non-degenerate triangle, non-degenerate again means vertices are not on the same line. We associate two circles. The incircle and the circumcircle. Now the incircle is the largest circle contained in the triangle. Let me make a picture. You may know from your previous math classes that the center of the incircle is the intersection of the three angle bisectors. Why do they intersect at one point? Well, the idea is the following. Whenever you have an angle, where are the points that are equidistant from the two sides of the angle. If a point is at the same distance from the two sides, there are infinitely many such points, and all of them, if you think about it, lie on the bisector of this angle. It's easy to explain why. The set of points in the plane equidistant from the two sides of an angle is precisely the bisector, the line bisecting the angle. And it's easy to explain why. If we take any point from this bisecting line, let's call it O, and project this point O on the sides of the angle, obtaining points Y and Z, then it's easy to see that the triangle XOY equals the triangle XOZ. Well, they're both right triangles. These are perpendiculars. And because this is a bisector, they have one of their acute angles equal. Any two right triangles with the same hypotenuse and equal acute angles are themselves equal. So it follows from here immediately that distance OY equals distance OZ. And so indeed, point O is at the same distance from the two sides. The converse statement is also true. If you take any point O prime that is equidistant from the two sides, then it's easy to argue that again these triangles x O prime y prime and x O prime z prime are equal. They're right triangles with a shared hypotenuse and equal legs. So everything else in these triangles is equal. In particular, this angle is equal to this angle. And so indeed point O prime must lie on the bisecting line. Let me recolor point O prime. I encourage you to think about points in the plane outside the angle. We're only talking about points that align inside the angle. But what happens if you take a point somewhere on the outside of the angle? All right, now that we know that the set of points equidistant from the two sides of the angle is precisely the points lying on the line bisecting this angle, we can explain where the center of the incircle is. After all, the center of the incircle must be equidistant from the three sides. So in particular, if I take a line bisecting angle A, and intersect it with the line bisecting angle B and call this point O. I see immediately that this point O is equidistant from AB and AC, and let this common distance be denoted by some D. Now, I claim this point is also a point line on the line bisecting angle C. Why is that? Well, we also have that the distance between O and line BC is D, because after all, point O line on the bisector of angle B has to be equidistant from the sides of the angle ABC. So this distance is also D. Now we see that this point O is equidistant from sides AC and BC. In other words, it's equidistant from the two sides of the angle C. It must therefore lie on the bisector of angle C. Hence, it follows that the three bisectors in a triangle, three lines bisecting the angles of the triangle, intersect at one point. It's common to denote the radius of the incircle by little r. That's what we're going to do. Instead of d, we will use little r. And again, this is called the incircle. The circle that touches the triangle internally at three sides. Its center is the intersection of the three lines bisecting the angles. The other important circle associated with the triangle is called the circumcircle. That is the smallest circle containing the triangle. As we will explain, the center of the circumcircle is the intersection of the three bisecting perpendiculars. Let's explain why. So let me draw a circle. And a triangle inside it. Also, I should note that the circumcircle, maybe I should add a page and move all that to the next page. I should also add that the circumcircle is the unique circle that passes through the three vertices of the triangle. Now, let me try to make it a little larger. So what do we have here? Where is the center of this circle? The center, wherever it is, must be equidistant from the 3 points, from the 3 vertices of the triangle. In particular, the distance between the center of this circle and point B and point A must be the same. Where in general? Let's ask this as a separate question. Given 2 distinct points, in the plane, where is the set of points, or what is the set of points? Let's name these points A and B. What is the set of points equidistant from A and B? Let's say this is A, this is B, and I claim that the set of points equidistant from A and B is precisely the bisecting perpendicular, i.e. the line that passes through the middle of the segment AB and is perpendicular to that segment. Any point C on that line I claim is equidistant from A and B. Let's prove this. The proof is very simple. So let's call this point O. Then I claim that the triangles AOC and BOC are equal. Why is that? Well, their right triangles share in one leg, and the other 2 legs are equal. I mean, the leg CO they share, and then AO equals BO. So we have that triangle AOC equals triangle BOC. Again, the explanation is that angle AOC equals angle BOC equals pi over 2. CO is shared, and AO equals BO because CO is a bisecting perpendicular. So it follows from the equality of these 2 triangles that AC equals BC. And so indeed, point C is equidistant from the points AB. The converse statement is also true. If I take any point C prime. So conversely, if C prime is a point in the plane equidistant from A and B, then C prime belongs to the bisecting perpendicular. Why is that? Well, we can form the triangle AOC prime and OC prime B, and despite my picture, I claim they must be equal. Why is that? Well, one side they share, OC prime is a shared side, AC prime equals BC prime because C prime is equidistant, and AO equals BO because both are equal half the distance AB. And from the equality of these two triangles, it should follow immediately that the triangle ABC prime is isosceles, and if you think about it, I encourage you to continue the argument. It will follow that C prime lies on the bisecting perpendicular. So the main point is, of course, that triangle AOC prime equals triangle BOC prime. And that, after very few steps, implies that C prime belongs to the line OC. Think about it. It's a nice exercise. Now, once we know that the set of points equidistant from the endpoints of a line segment is precisely the line that is bisecting perpendicular, we see that in this triangle ABC, if I take a bisecting perpendicular to the line to the side AB, and a bisecting perpendicular to the side AC, and intersect them, they must intersect, because if they were parallel, then the corresponding sides AB and AC would be parallel, which we know cannot happen because the triangle is non-degenerate. Now, let's denote this point by O, the point of their intersection. We see that point O is equidistant from the points A and B. That is because that point lies on the bisecting perpendicular to the side AB. But because it also lies on the bisecting perpendicular to the side AC, it's also equidistant from points A and C. Because of that, we conclude that the point O is equidistant from points B and C. this distance equals this distance equals this distance. All three distances are equal. But that implies, as we have just explained, that point O also lies on the bisecting perpendicular to the side BC. Again, be sure to explain that the converse of this statement here is true, namely that if C prime is a point in the plane equidistant from A and B, it necessarily lies on the line that is bisecting perpendicular to the segment AB. It's very, very easy. All you need to do is show that this angle and this angle are both pi over 2, 90 degrees. All right, once we have explained that the center of the circumcircle, the center of the circle passing through the three vertices of the triangle, is the intersection of the three bisecting perpendiculars, and the three bisecting perpendiculars intersect at one point, which is the center of this circumcircle, we introduce the notation capital R. That will be the radius of the circumcircle. So lowercase r is the center of the incircle, uppercase R is the center of the circumcircle. All right. Also, I encourage you to pick up your favorite geometry book and read about the fact that orthocenter, the point that every triangle has an orthocenter, the point where all three heights intersect. So they intersect at one point. In any triangle ABC, we will denote heights by h with the lowercase corresponding to what side that height drops on. For instance, this will be HB, this will be HA, and this will be HC. Again, in any triangle, the heights intersect at a single point. Known as orthocenter. As always, the area of any triangle will be denoted by capital S, and by lowercase p we will denote half the perimeter, sum of the sides ABC divided by 2. Our first big result is the law of sines. But before we get to the proof of the law of sines, we need to prove another auxiliary result concerning angles related to a given circle. Well, let us first of all recall that we measure angles by the length of the associated arc in a circle. More precisely, if we remember how we define the concept of 1 radian, what's an angle of 1 radian? When do we say that this angle is 1 radian? It means that if we draw any circle centered at the vertex of this angle, then 1 radian, this angle will be 1 radian if the length of the corresponding arc, when this angle viewed as the central angle, this here is the center of the circle, when the length of this arc equals the radius. So in fact, a central angle is measured by the arc contained between its sides. We can measure any angle in a circle, any central angle. Central angle is an angle whose sides are the radii of a circle. If we have a circle, we can measure every angle, every central angle, by the associated arc. Of course, we have an understanding here that we have this angle, and it's measured by this arc. And we also have this angle, which is measured by this arc. In fact, if the radius is 1, if we have a unit circle, the length of the arc equals the measure of the angle. Say, for instance, the length of the entire circle is 2 pi, and the entire circle corresponds to the central angle of 2 pi. Half the circle corresponds to half the circumference of the circle, whose length is pi, and that is indeed an angle of 180 degrees. So that is a very important idea. A central angle is measured by the arc contained between its sides. We're going to be measuring angles by arcs. So our next result is concerned with the so-called inscribed angles. An inscribed angle is an angle formed by two chords with a common point. Say, for instance, look at this circle. AE and AD, for instance, are two chords in this circle with a common point A, and so the angle EAD is an inscribed angle. Of course, the angle BAC is also inscribed, or BAD is inscribed. BOC, by contrast, is a central angle. So the theorem here is very simple. The measure of an angle inscribed in a circle equals 1/2 the arc contained between the sides. For example, here the angle EAD equals 1/2 the arc contained between its sides. So that's the arc I can say EBCD. Arcs will be denoted by this symbol, EBCD. Likewise, say the angle BAC, which is inscribed, is half the arc BC. Of course, we have to understand, and it's an important comment here, that there are two arcs with endpoints BC, this arc and this arc. We always mean that arc that doesn't contain the third point A. So we really mean this arc. It's interesting that this comment here is important, that if we had the other arc, let me draw a circle, the big one, the major arc, say this is B, this is C. If we take this arc, then an angle that is inscribed into this circle and that is subtended by this arc will be obtuse. It will, for instance, be this one. BAC is an inscribed angle, and this here is the arc, again, the one, we have two arcs, this one and this one. We always need the one that doesn't contain the third point, A. In this situation, it's this big arc. It's this one that doesn't contain point A. And indeed, the statement makes sense because the inscribed angle is half the arc subtended. In our picture, the angle is obtuse, it's more than 90 degrees, so the arc must be more than 180 degrees. And it's clear from the picture that indeed that arc is greater than half the circle. The second part of the statement follows from the first one. Because the inscribed angle is half the arc contained between its sides, and an arc measures the corresponding central angle, it follows that an inscribed angle is half the central angle subtending the same arc. For instance, as we will see here, as we will prove in a minute, the angle BAC is half the angle BOC. Likewise, the angle BAD is half the angle BOD. Have this angle. BAD, for instance, if BAD is 30 degrees, BOD would be 60 degrees. All right, let's look at the proof. We consider three different cases, depending on whether one of the two sides of the inscribed angle passes through the center. That's the first case. In the second case, the center of the circle O will be inside the angle. This angle will be BAD. And in the third case, the angle will be EAB, in which the center of the circle is outside the angle. Clearly, these are the only three cases that could happen. Whatever angle you take, either one of the sides contains the center, or the center is inside the angle, or the center is outside the angle. So our arguments will be slightly different in these three cases. So let's look at case 1. One of the sides of our inscribed angle, BAC in this case, contains the center. Well, let's join B and O like in our picture. Now we see immediately that the triangle we see that the triangle AOB is isosceles, because here BO equals AO equals the radius of the circle. Now this implies that the two angles adjacent to the base of the triangle are equal. So the angle BAO equals the angle ABO. Okay. Now we need to relate the angle BAO to the angle BOC. How do we do this? Well, the three angles in this triangle AOB add up to pi. So angle BAO plus angle ABO plus angle BOA add up to pi, and these two angles are equal, BAO and ABO. So we have that 2 times angle BAO, which is the same as BOC, simply is pi minus the angle BOA. But pi minus the angle BOA is exactly the angle BOC. So from here, if we divide this by 2, the angle BAO, which is the same as BAC, is 1/2 the angle BOC, which is of course 1/2 the arc BC. And this finishes the proof of the first case. The angle BAC is half the angle BOC. Now the other two cases are reducible to the first case. So in the second case, the center O is inside the angle. Say, consider the angle BAD. With respect to that angle BAD, the center O is inside the angle. Our goal is to prove that BAD is half the angle BOD. Well, the idea is this. We again construct a line joining A and O, and let C be the intersection of that line with the circle, other than A. We know already that from the first case, we know that angle BAC is 1/2 the arc BC, and also the angle CAD is 1/2 the arc CD. Now, the desired angle BAD simply is the sum of BAC and CAD. And in fact, we just take these two equalities and add them up. So we get angle BAC plus angle CAD equals 1/2 arc BC plus 1/2 arc CD. On the one hand, angle BAC plus angle CAD is angle BAD. On the other hand, if we factor out here 1/2, arc BC plus arc CD equals, of course, arc BD. So that's 1/2 arc BD. Or in other words, 1/2 angle that subtends that arc, BOD. And finally, case 3. When the center of the circle is outside the inscribed angle. Say, take angle EAB. Idea is like in the previous case, we join A and O by a line giving us point C. And we see here that angle EAC equals half the arc EC. From case 1, angle EAC equals half the arc EC. And likewise, angle BAC equals half the arc BC. Now, if we subtract one from the other, if we subtract this from this, subtracting the second equation, from the first equation, we get what? We get angle EAC minus angle BAC. That is the difference of the left-hand sides. On the one hand, angle EAC minus angle BAC is precisely the angle EAB. On the other hand, on the right, we have 1/2 arc EC minus 1/2 arc BC equals 1/2 times arc EC minus arc BC, and of course arc EC minus arc BC is simply arc EB. That is what we needed to prove, because arc EB is precisely the central angle EOB. So that is a very useful statement. We will need it in our proof of the law of sines. So here is the statement of the law of sines. The ratio of any side of a triangle by the sine of the opposite angle is constant, and moreover it equals the diameter of the circumcircle. You can also memorize this in a slightly different way, because from here I can write that, say, A equals 2r sine A, or B equals 2r sine B, or C equals 2r sine C, and the theorem can be restated in the following way. In any triangle, the length of any side equals the diameter of the circumcircle times the sine of the opposite angle. As you see, capital A is the angle opposite to lowercase a. This is lowercase a. This is capital A. This is capital B. Angle B, this is lowercase b. Now, how do we prove this? Well, in the picture you see a triangle with all sides obtuse, with all sides acute. So I encourage you to check this proof. For the right triangle and the obtuse triangle. All right. In our situation, when all angles are acute, the proof is the following, and it will remain for the other two cases. So here is the triangle ABC. O is the center of the circumcircle. let OD be perpendicular to the side BC, and let E be the intersection of BC and OD. So what happens, we simply drop the perpendicular from the center O to the side BC, and let D be a point of intersection of that perpendicular with the circle, and let E be the point of intersection of OD with the side BC. Now, first of all, I claim that if we join O and C, I claim that the triangles BOE and triangle OEC are equal. Why is that? Well, they're right triangles, they share a leg, and their hypotenuses are equal as radii of the circumcircle. The right triangles, they share the leg OE, and their hypotenuses BO and CO are equal. Since both are the radii of the circumcircle. In particular, from here, it follows that point E is the middle of the side BC. Because BE equals CE, right? These sides are equal. This side is shared, so the other sides are equal. BE equals CE equals A over 2. And also something else is interesting. We have that angle BOD equals angle EOC, as angles lying opposite equal sides in equal triangles. BOD equals angle DOC. And therefore angle BOC simply equals twice the angle BOD. Now, let's talk about the angle BAC. The angle BAC is inscribed, and by the result of the previous paper, of the previous page, the angle BAC equals half the corresponding central angle BOC. By the previous theorem, the angle BAC equals half the angle BOC. And angle BOC is twice the angle BOD. So we have proved that the angle BAC equals the angle BOD. But angle BOD is involved in a right triangle. And so we can express it using some trigonometry. From the triangle BOE, it follows that, say, sine of the angle BOD equals the opposite leg BE by the hypotenuse BO. So opposite over hypotenuse. Opposite leg is BE. Hypotenuse is BO. BE we know is A over 2. And BO is the radius of the circumcircle. So it follows from here that A equals 2R sine of the angle BOD. But as we have explained, the angle BOD equals the angle BOC, which is simply A. So from here it follows that A equals 2R sine of BAC, or simply A. Again, it won't hurt to repeat the argument. We have our triangle ABC. We also show the center of the circumcircle, capital O. So this distance is the radius. We also join O and C. So OC is also the radius. We quickly note that the triangles OBE and OEC are equal. Why is that? Both are right triangles, because by construction OD was a perpendicular dropped from point O. OBE and OEC are right triangles in which hypotenuses are equal. Both are the radii of the circumcircle. This leg is shared, and therefore everything else in these triangles is equal. In particular, BE equals EC, so point E is the middle of the segment BC, and therefore BE equals A over 2. Also, the angles BOD and DOC as line opposite equal sides in equal triangles are equal. So that implies that the angle BOC is twice the angle BOD, because these two are equal. Now, our desired angle A is an inscribed angle. The arc that subtends that angle is the arc BC. We see that the central angle BOC also is subtended by this arc. So we know that the angle BAC is half the central angle BOC. But half the central angle BOC is, for instance, the angle BOD. So we come to the conclusion that the angle BAC equals the angle BOD. Now we work with the angle BOD using the right triangle BOE. In this right triangle, sine of the angle BOD is the opposite leg, A over 2, divided by the hypotenuse, which is R. From here it follows that the opposite leg, A over 2, equals R times sine of the angle BOD. In other words, that A equals 2R sines of angle BOD. And since angle BOD is simply A, we have proved that A equals 2R sine A. And of course, by the same argument, you can show that B equals 2R sine B, and lowercase c equals 2R sine C. Again, the picture assumes that our triangle is acute. I encourage you to check this proof, which should work in the other two situations when the triangle ABC is a right triangle. It's interesting, by the way, that in this situation, the circle passing through the 3 points, the circumcircle, will have the hypotenuse as a diameter. Think why. In this particular case, AB will be the diameter of the circumcircle. In particular, the center of the circumcircle is precisely the midpoint of the hypotenuse. And now, likewise, the proof works just fine if you consider an obtuse triangle. Nothing should really change. But do check the details. And let me know if you have any questions here. The next, our second big result about metric relations in a triangle is the so-called law of cosines, which states that the square of one side in a triangle equals the sum of the squares of the other sides minus twice their product times the cosine of the angle between them. Note, by the way, that in my picture, angle C is obtuse, so cosine C will be negative, with another negative sign in front of it. Negative cosine C will be positive. And so, in my picture, this will be greater than, this will be a positive quantity, negative cosine C. You are familiar with one particular case of this theorem. When C is a right angle. This theorem gives that C squared equals A squared plus B squared minus twice AB cosine pi over 2. And because cosine of pi over 2 is of course 0, we simply get A squared plus B squared, known to you as Pythagorean theorem. So in a certain sense, the law of cosines is a generalization of Pythagorean theorem. Generalization. And again, in my first picture, I have C over pi over 2. C is an obtuse angle, so cosine C is negative. So negative cosine C is positive. So I will have C squared equals A squared plus B squared minus 2AB cosine C. And so this will be greater. The whole thing, negative 2AB cosine C, will be positive. So this will be greater than A squared plus B squared. Naturally, when C is less than pi over 2, we will have C squared equals A squared plus B squared minus 2AB cosine C. This time cosine C will be positive. And so negative 2AB cosine C will also be positive. And if we neglect this, we will get a quantity less than A squared plus B squared. We will look at some other applications of the law of cosines on the next page, but now we have to prove it, and to prove it, we first prove another useful result about some properties of projections. So the result is this. In any triangle ABC, as we know, angles are also ABC. Sides are lowercase abc. There holds, for instance, that A equals B times cosine C plus C times cosine B. And likewise, the other two identities that come from here by cyclically replacing A by B or A by C. So let's prove this one. Let's assume for certainty that angle A is acute and project point A, vertex A, on the line BC. We don't know whether angle C is acute, right, or obtuse, so we don't know whether point D, the projection of A onto BC, will be between B and C, outside the interval BC, like here, or will project exactly into the point C. But we do know that, say, in the first case, we have BC, which is A, clearly is BD plus DC. In the second case, BC equals BD minus DC. And in this case, BC simply equals BD. Now, BD in all three cases is easy to express because this here is C. So in all three cases, we have BD equals C cosine B, right, in this triangle. BD equals C cosine B in this triangle. BD equals C cosine B. And in this triangle, BD equals C cosine B. What's different is the expression for DC. If we write the expression for DC in case 1, DC simply is B times cosine C in this triangle. DC equals hypotenuse B times cosine C. In the second case, it'll be different because in this right triangle, if we write DC, it'll be all right. So which right triangle? Yes, this right triangle. It'll be hypotenuse B times cosine of this angle, ACD. But ACD is clearly pi minus angle BCA, right? ACD is pi minus BCD, but BCD is simply C. And we know that cosine pi minus c equals negative cosine c. And in case 3, dc is simply 0, and I can write this as b times cosine c, because cosine c in this case is 0 because c is pi over 2. Now it's easy to check that in all 3 cases, when you add BD plus DC, right? BD is again C cosine B. In the first case, when you add BD and BC, C cosine B plus B cosine C, you get A. In the second case, we get A equals BD minus DC. So it's going to be C cosine B minus negative B cosine C. We again get positive B cosine C plus C cosine B. I mean, if you want to get very detailed, we can write in case 1, A equals BD plus DC, and that is C cosine B plus B cosine C, as claimed. In the second case, we get A, which is BD minus DC, and BD is C cosine B, and DC is negative B cosine C. And that is B cosine C plus C cosine B as claimed. And in the third case, again, we get A equals BD, which is C cosine B, and I can add here, I can write that C cosine B equals C cosine B plus B cosine C, because B cosine C is 0 anyway. Again, as claimed. So in all 3 cases, we get the desired result, that A equals B cosine C plus C cosine B. So the pattern is very clear. You have one side on the left, the other 2 sides on the right, and each side on the right is multiplied by the third remaining angle. So these identities allow us to very quickly prove the law of cosines. So we take these identities, again, A equals B cosine C plus C cosine B, B equals A cosine C plus C cosine A, and C equals A cosine B plus B cosine A. Then if we multiply the first of these by A, we get a squared equals ab cosine c plus ac cosine b. The second identity multiplied by b yields b squared equals ab cosine c plus bc cosine a, and multiplying the third identity by c yields that c squared equals ac cosine b plus bc cosine a. And now we should compute a squared plus b squared minus c squared and see what this yields. So a squared is ab cosine c plus ab cosine b. B squared is ab cosine c plus bc cosine a. And c squared is ac cosine b plus bc cosine a. So when you do the algebra, you see, for instance, that AB cosine, okay, it should be AC here. That AC cosine B and negative AC cosine B cancel out. And likewise, BC cosine A and negative BC cosine A cancel out. And the remaining two terms combine. AB cosine C and AB cosine C yield 2AB cosine C. And of course, now the result follows, because from here we get that c squared equals a squared plus b squared minus 2ab cosine c as claimed. So again, this result is a kind of generalization of the Pythagorean theorem. In particular case, when angle C here is pi over 2, we simply get the Pythagorean theorem, and of course the side opposite to the angle that is pi over 2 is indeed its square equals the sum of the squares of the other two sides. One of the first important applications of the law of sines and the law of cosines is solving triangles. To solve a triangle means to find all three sides of the triangle and all three angles. Typically, in a problem where we need to solve a triangle, we'd be given some of its sides and some of its angles, and we need to find the remaining ones. There are three classical situations here. We know one side of the triangle and two adjacent angles. For example, we know side C and adjacent angles A and B. We need to find the unknown angle C and the unknown sides AC and BC. Well, that's easy to do using the law of sines. Of course, the remaining angle is simply pi minus A minus B. And to find the sides AC and BC, we use the law of sines. For example, B divided by sine B, B divided by sine B equals C divided by sine C, because both quotients are equal to the diameter of the circumcircle. From here, it's easy to find B. B is simply C over sine B times sine C. It's a typo, of course. So from here, B equals C over sine C times sine B. And the same for side A. A over sine A equals C over sine C, because both quotients are equal to the diameter of the circumcircle. And from here, it's easy to find A. A is C times the sine of the ratios. Another situation that's very common. When we have two sides and the angle between them known. We know, say, sides A and B. And the angle between them, which is of course C. We need to find the other two angles and the remaining side AB. To find the remaining side C, we can use the law of cosines. By the law of cosines, that side is root of the sum of the squares of the known sides minus twice the product of these sides times cosine of the known angle C. And once we know C, we can again use the law of sines to write that A over sine A equals C over sine C, and the same for B. That gives us sine A and sine B. This is just to be okay. So we know sine A and sine B. If these ratios here are by absolute value greater than 1, then the problem has no solution. By the way, I should have also checked this. I should have also checked whether this quantity is non-negative, because if it's negative, the problem has no solution. I should add this here. If a squared plus b squared minus 2ab cosine c is negative, then of course the problem has no solution. If these expressions, one of them by absolute value is greater than 1, of course there is no solution because sine A and sine B by absolute value have to be at most 1. Suppose now that both are by absolute value less than or equal to 1, but then there are two different cases, whether angle C that we know is obtuse or acute. If it's obtuse, if it's greater than pi over 2, then both angles A and B are between 0 and 90, and we can find them by taking arcsine of these expressions. But if angle C is between 0 and pi over 2, one of the angles A and B may be greater than pi over 2. And why is it important? It's important because if one of these angles, say A, is greater than pi over 2, it's false, then A is arcsine of sine A. Arcsine is always in between negative pi over 2 and pi over 2. So you need to know whether A and B are less than pi over 2 or greater than pi over 2. You may want to find cosine A from this, again, using the law of cosines. If you take law of cosines, write it in the form a squared equals b squared plus c squared minus 2bc cosine A. From here, of course, cosine A will be b squared plus c squared minus a squared over 2bc. And now, in fact, you don't need any of that at all. You don't need any of that at all. You can find cosine A like this, and then just take, yeah, you don't need any of this at all. You find C, then you find cosine A, and then A is immediately from here arc cosine of this expression, cosine A. And the same with B. B is arc cosine of cosine B, and that should be a squared plus c squared minus b squared divided by 2ac. Yeah, finding cosine is much better than finding sine, because when you have cosine, you can just take arc cosine. You don't need to know where your angle is. And now when the three sides are known, the other classical situation. So one side and two adjacent angles are known. The other situation is when the two sides and the angle between them is known. And the third situation is when the three sides are known. So we know A, we know B, and we know C. And of course, here we can just again use the law of cosines. We can write that c squared equals a squared plus b squared minus 2bc cosine c. And from here we can find c as arc cosine of a squared plus b squared minus c squared divided by 2ab. And likewise, a squared equals b squared plus c squared minus 2bc cosine a, and b squared equals a squared plus c squared minus 2ac cosine b. So from here we can find a, that is arc cosine. B squared plus c squared minus a squared over 2bc. And from here we can find b. B is arc cosine of a squared plus c squared minus b squared over 2ac. There will be, in numerical examples, other situations, but these three are the most common, and in these three the solution is always unique. So what's left to do is to look at some numerical examples. In the first of these numerical examples, we are given a problem where we need to solve the triangle shown in the figure. And what do we have here? We have one side known, and we have two angles known, which of course means that we are given all three angles because the three of them must add up to pi, alpha plus beta plus gamma must be 180 degrees. Therefore, beta from here is 180 minus alpha minus gamma, which is 180 minus 50 minus minus 30 degrees, which is 100 degrees. So this is an obtuse triangle. Angle beta is over 90 degrees. All right, so once again, beta equals 100 degrees. Now we can find the side that we don't know, for example, by using the law of sines. Or law of cosines, it doesn't really matter, although law of cosines won't work here. So we do need to use the law of sines. So we use the law of sines. Can we, for instance, try to find b using the law of sines? Let's see. So using the law of sines, we have b over sine beta equals c over sine 30 degrees equals a, which is 10, over sine 50 degrees. So we don't really need the middle part. We need this and this. So we know a, that's 10. And from here we can immediately find, actually we can find both b and c. So from here, b equals sine beta over sine 50 degrees times a. So b equals sine of 100 degrees over sine 50 degrees times 10. And likewise, c equals sine 30 degrees, which is 1/2, over sine 50 degrees times a. So c equals a over sine 30 is 1/2, so this can be simplified. So c equals a over twice sine 50 degrees. By the way, the expression for b can be simplified. So b being sine, this I meant of course was, okay, so let's simplify both, b and c. So b is sine 100 degrees over sine 50 degrees times 10. Using the sine of the double angle formula, sine of 2 alpha equals 2 sine alpha cosine alpha. So if I apply this here, it'll be 2 sine 50 degrees cosine 50 degrees over sine 50 degrees times 10. And so sine 50 degrees and sine 50 degrees cancel out. And I get 20 times cosine of 50 degrees. That's b. I should erase the. And likewise, I can simplify c, which is sine 30 degrees over sine 50 degrees times a. That is 1/2 sine 50 degrees times 10. So that is 5 over sine 50 degrees. It's interesting to verify our findings using the law of cosines. So let's verify our computations using the law of cosines. So by the law of cosines, we must have a squared equals b squared plus c squared minus 2ab, cosine of the angle between a and b, cosine of the angle between b and c, sorry, which is alpha, 50 degrees. So it should be that the right-hand side is 10 squared because a is 10. So the right-hand side better simplified to 100. So we have b squared (20 times cosine 50 degrees squared) plus c squared 5 over sine of 50 degrees squared minus 2 times 20 cosine of 50 degrees times c 5 over sine of 50 degrees times cosine of alpha. Cosine alpha is 50 degrees. Somehow this should simplify to 100. Let's see how. So we get 400 cosine squared 50 degrees plus 25 over sine of 50 degrees squared minus 2 times 5 is 10 times 20, 200 cosine squared of 50 degrees over sine of 50 degrees. Alright, now common denominator is sine squared 50 degrees. And so we get 400 sine squared 50 degrees cosine squared 50 degrees plus 25 minus 200 sine 50 degrees cosine squared of 50 degrees. Doesn't seem too obvious how to simplify this. Alright, perhaps I can get back to sine 100 degrees, or I can factor out 200 sine 50 degrees here. There are different ideas. If I factor out 200 sine 50, what will I get? I will get 2 sine 50 degrees cosine squared 50 degrees minus cosine squared 50 degrees. Maybe I should even factor out both. (200 sine 50 degrees cosine squared 50 degrees). In parentheses, I will get 2 sine 50 degrees minus 1. Yeah, not exactly clear how to simplify this. I encourage you to find the argument that shows that this fraction here, or this one, doesn't matter, simplifies to 100th. So we have in fact solved this problem correctly, and it would be nice to verify that the found sides, B and C, along with the node side D, satisfy the law of cosines. It's some kind of trigonometric argument, and I'm leaving this for you as homework. In the next problem, we are also not in one of the three classical situations because we are known three sides, and we're known two sides, and the angle that we know is not between them. We don't know angle gamma. So we should improvise, and perhaps we could find beta by using the law of sines. We can write that 6 divided by sine 35 degrees equals 8 divided by sine beta. From here, sine beta is 8 times sine 35 degrees divided by 6. Or simply that sine beta equals 4 sine 35 degrees over 3. Now, if we simply write that beta equals arcsine of that number, that would be a mistake because that number certainly belongs to the interval 0 pi over 2. However, we see from the picture that beta appears to be an obtuse angle. So in fact, beta is not that number. Beta is pi minus that number. Because pi minus that number is between pi over 2 and pi. And note, by the way, we wouldn't be able to solve this problem if we didn't see the picture. So our solution relies on the picture. So this gives us beta. Of course, then gamma is simply pi minus alpha minus beta, and we can write alpha in radians. So alpha is 35 degrees. Remember, 360 degrees is 2 pi radians. So 1 degree is 2 pi over 360 radians, or pi over 180. So 35 degrees is 35 times pi over 180. There's some cancellation here because 35 is 5 times 7. And here we have 180, which is, say, 90 times 2. 90 is divisible by 5, that's 18. And so this is 7 pi over 36. So we can write that gamma is pi minus 7 pi over 36 minus beta, which is pi minus arc sine 4 sine 7 pi over 36 over 3. And of course, pi and negative pi cancel out. So we find that gamma equals arc sine of 4 sine 7 pi over 36 over 3 minus 7 pi over 36. Now, to find the third side, we can use the law of cosines, for instance, or law of sines. It doesn't really matter. By the law of sines, let's call that sines x divided by sine gamma equals, for instance, 6 divided by sine of 35 degrees. So from here, x is 6 sine gamma over sine of 7 pi over 36. And you can directly plug this into our expression. So x is 6 sine of arc sine 4 sine 7 pi over 36 divided by 3 minus 7 pi over 36 divided by sine of 7 pi over 36. And you can probably simplify this, although the expression is likely to have square roots at the end. If we take 7 pi over 36 as y for brevity, we can then write this as 6 sine of arc sine of 4/3 y minus y over sine y, and using the sign of the difference formula, that gives us sine of arc sine of thirds y times cosine y minus cosine of arcsine of 4/3 y times sine y over sine y. And of course, sine of arcsine is just the argument. So we get 6 times 4/3 y times cosine y. Now, how do we simplify this? Cosine of arcsine. We did this in the past. Cosine of arcsine of something, some alpha. I can write cosine as plus minus 1 minus sine squared. Because arcsine is always is either quadrant 1 or quadrant 4 where cosine is positive. I should take the positive sign here, and so that should be square root of 1 minus alpha squared with a positive sign. So I get here a root of 1 minus 4/3 y squared times sine y over sine y. Again, it's questionable if this simplification is valuable, because if we multiply the top and the bottom by 9, for instance, so we get 12y cosine y. Maybe not by 9. Yeah, 9 is good. Then 9 is multiplied by this squared. Maybe I should multiply by 81. If I multiply this by 81, if I multiply this by 9, yeah, I think I should have multiplied it simply by 3. Because this here is square root of 1 minus 4y squared over 9, which is 9 minus 4y squared over 3. If I simply multiply this by 3, not by 9, I will get 4y cosine y minus root 9 minus 4y squared sine y. Again, it may be difficult to see the point of this simplification. But anyway, we do get some kind of answer. 6 times 4 times 7 pi over 36 times cosine of 7 pi over 36 minus root of 9 minus 4 times 7 pi over 36 squared times sine of 7 pi over 36. By the way, when I multiply this by 3, I could cancel, right? Make this 2. So what's left in the denominator is sine of 7 pi over 36. Here there shouldn't be any ambiguity. The only ambiguity in this problem was when we found beta. Because again, if you look for, we can't use the law of cosines here. We are bound to use the law of sines. And when we do this, we need to take arcsine. But arcsine gives the result as if angle beta was acute. In our picture, however, angle beta is obtuse. So another angle whose sine is 4 sine 35 degrees over 3 is not this arcsine, but pi minus that arcsine. And the rest is easy. Once we find beta, we quickly find gamma. Once we find gamma, we can find the remaining side x. So the only interesting point in this problem is that we use the picture when we replaced arcsine by pi minus arcsine. Other than that, the problem is quite trivial. Although, again, I should emphasize that there are possibly 2 triangles with an angle of 35 degrees, adjacent side 8 and opposite side 6. One triangle is this one. The other triangle is this one. If this side is 6, right? So I may also have this triangle 8, 6, and 35 degrees here. The difference between them is that in our triangle given, because beta is an obtuse angle, or rather we made it, or we decided to take beta to be obtuse as shown in the picture. This angle here, gamma, is necessarily an acute angle. And so when we compute gamma, we should check that gamma is indeed less than pi over 2. Because in this triangle, this angle gamma prime will be greater than pi over 2. And that is quite interesting. So again, use the picture because in this problem we have 2 triangles satisfying the given conditions. But if we use the given picture, then we can exclude this one. There is no ambiguity anymore. All right, in the next problem, again, we use the law of sines. To write that 12 divided by sine of 85 degrees equals 9 divided by sine beta. So then sine beta equals 9 times sine 85 degrees over 12. Beta appears to be an acute angle, so beta is simply arcsine of that number, and you can compute it to be roughly 48.3 degrees. And this time there is no ambiguity here, because even if we didn't have the picture, because if you try another possible solution, pi minus that, so if beta were 180 minus that, so that's 131.7 degrees. Then the third angle, alpha, would be 180 minus beta minus 85 degrees. And that is already less than 0. So, of course, that's not possible, so beta is indeed 48.3 degrees. And alpha, in fact, is 180 minus beta minus 85. So that's 180 minus 48.3 minus 85. So that is approximately 46.7. So we know two sides, we only need to find side A. To find side A, we again use the law of sines. So we can write (12 over sine 85) equals A over sine alpha. So that's A over sine 46.7 degrees. So from here, A roughly is 12 times sine of 46.7 degrees divided by sine 85 degrees. That's roughly 8.8. And in this problem, we don't have any ambiguity. In the next problem, we're not given any picture. We need to find all possible triangles if one side has length 4 and its opposite an angle which is 50 degrees. And a second side has length 10. So we have in our triangle an angle of 50 degrees, and the side opposite to it is of length 4. Of course, there are multiple ways how this can happen, like this, like that. Hard to say. So this side is 4, and some other side is 10. Again, it doesn't matter how this happens. Maybe like this. This side is 4, this is 50 degrees. Maybe this side is 10. Or maybe like this. This side is 4. And then this side is 10. Or this side could be 10. Or this side could be 10. Or this side could be 10. Doesn't matter. Either way, in either situation, or in fact, in other situations not shown by the law of sines, we have that 4 divided by sine 50 equals 10 divided by sine of an angle opposite to 10. Let's call it alpha. Therefore, sine alpha equals 10 sine 50 over 4. And that is roughly 1.915, which is greater than 1. Of course, no angle alpha can deliver that value for sine, so the answer is immediately that there are no such triangles. We now show how trigonometry is used to derive various formulas for the area of the triangle. We will derive a whole bunch of them. Remember, S here is area. The first formula that we derive is that the area of a triangle is 1/2 one of its sides times the length of the height dropped on that side. So the picture is this. Area is 1/2 A times HA. Well, the idea is this. First, we show that the area of a parallelogram is the product of one side times the height dropped on that side. So consider a parallelogram. Remember, a parallelogram is a four-gun with both pairs of sides parallel. So in particular, AD is parallel to BC, and AB is parallel to CD. So what we're going to explain is that the area of this parallelogram is, say for instance, AD times the height h dropped on the side AD. The argument is very simple. We construct a point P by dropping the perpendicular on AD from C and argue that the triangle ABX and CDY are equal. It should be fairly simple. They have equal angles, they are right triangles, and they have equal hypotenuses. AB equals CD. Now, from the equality of these two triangles, it follows immediately that the area of this parallelogram simply is the area of this rectangle. Because if I were to cut this triangle ABX and put it in here, I would obtain the rectangle here. So it follows that the area of the parallelogram ABCD equals the area of the rectangle BCYX, which of course is the product of two sides, xy times bx. Bx is h. What's left to do is explain that xy equals AD. Well, that should be fairly simple because if you call this, for instance, by t, this piece, then by the equality of the triangles, this piece is also t. So we have AY being AX plus so I don't really need this. All I need to explain is that, okay, so yes, AD equals AX plus XD, and AX is T. And at the same time, XY equals XD plus DY. DY is T. So we have that AD equals XY. So we have that the area of the parallelepiped ABCD equals AD times H. Now, why is that important? That is important because the area of the triangle ABC will be equal to half the parallelogram built upon it. How do we build a parallelogram? Well, we draw a line through A parallel to the side BC, and likewise we draw through B a line parallel to the side AC. Let's call this point D. I claim that the triangle ABC equals triangle ABD. Why is that? Well, they share one side. AB, for instance, is shared. And then we have equality of angles. Which ones? Which ones? So we have this parallel to this. Okay, so what can we say? If this angle is, say, alpha, this also is alpha. And therefore this is alpha, and therefore this is alpha. And okay, so angle ACB equals alpha and equals angle ADB. And we can probably argue the same thing about the other angle in triangle ABC. Let's think which one. So we have parallel lines here. This angle, for instance. Or perhaps this angle. Let's call this beta. Where else do we have beta? This is beta. No, we also have this beta. And therefore this also is beta. So we have that angle ABC equals angle DAB. So this explains that triangles ABC and ABD are equal. And of course, ADBC is a parallelogram by construction. So from the picture, we see that the area of the triangle ABC, which is just S, equals half the area of the parallelogram ADBC. But how to find the area of the parallelogram we know. That simply is one side, say BC, times height. And that proves this first part. The area of a triangle equals half base times height. Alright, so this part is done. The next formula. The area of a triangle equals half the perimeter times the radius of the incircle. How does that follow? Well, let's draw a triangle with an incircle. Alright, so let the triangle be as always ABC. So the center of the circle is some point O. So suppose the points at which the circle touches the sides of the triangle are A1, C1, and B1. So that the distance OA1, OB1, and OC1 is R. Now if we join O and the points A, B, and C, we see immediately that the area of the triangle ABC can be written as the area of these three triangles, ABO, BOC, and AOC. And area of each of these triangles is easy to compute because, say, in triangle ABO, base is C, and height is R. Right? Distance OC1, OB1, and OA1 are all little r. So in each triangle I can write that the area is 1/2 base times height, where base is the side of the triangle and height is the radius. Now AB is simply C, BC is simply A, and AC is B. And of course, if I write this as R times A plus B plus C over 2, I see that this is P. All right, so that proves the second formula. Now, the area of a triangle equals the product of the three sides divided by the product of 4 and the radius of the circumcircle. Note, by the way, the units in this formula. When you write S equals ABC over 4R, the units will be what? A, for instance, is in meters, B is in meters, and C is in meters. But then radius is also in meters. So we do get meters squared as expected. It's very important that we check that the units are the units of area. For otherwise, this doesn't make any sense. Perhaps it's easier to first show this formula, that the area equals 1/2 product of two sides times the angle between them. Let this be my number 3. All right, let me draw again a triangle. So this is A, this is B, this is C. This is HB, the height. And from this triangle, I don't know, let's denote this by P. From the triangle BCP, we immediately find that BP, which is of course H, is hypotenuse A times sine of the angle opposite to H, which is C. And therefore, the area, which is half base times height, will be 1/2 base times, instead of height, I write expression for height, A sine C. And so this proves that formula. It's all very important. This formula follows immediately from the law of sines, 3 and 4. So from the law of sines, c divided by sine c is the diameter of the circumcircle. So from here, sine c is c divided by the diameter. And if I plug this into the formula I just obtained, I get 1/2 AB times, instead of sine c, I write c over 2r. Of course, that is just sine c. And that gives me ABC over 4r. So this will be my number 4. And number 5, the so-called Heron's formula. Will require a little bit of algebra and law of cosines. So we already know that S equals 1/2 AB sine C. And so if I multiply this by 4, I get 4S equals 2AB sine C. And also by the law of cosines, I have c squared equals a squared plus b squared minus 2ab cosine c. The picture won't hurt. From here, I get that a squared plus b squared minus c squared equals 2ab cosine c. And now I need to work with these two identities. It makes sense to square them up and add, because on the right we will get sine squared and cosine squared, and sine squared plus cosine squared is 1, so that's good. So we square the highlighted identities and add them. So what do we get? 4s squared equals 2ab sine squared c. That's the square of the first identity. That means 16s squared that should be sine c squared equals 4a squared b squared sine squared c. And the second identity, a squared plus b squared minus c squared equals 2ab cosine c squared, which of course is simply 4a squared b squared cosine squared c. Now we add them, namely this one and this one. So when we add them, we get 16s squared plus a squared plus b squared minus c squared equals 4a squared b squared sine squared c plus 4a squared b squared cosine squared c. And naturally, when on the right we factor out 4a squared b squared sine squared plus cosine squared add up to 1. And so we end up with 16s squared plus a squared plus b squared minus c squared equals 4a squared b squared. And now a little bit of algebra. From here we express 16s squared as 4a squared b squared minus a squared plus b squared minus c squared. Now, difference of squares. Remember the formula that we use all the time. U squared minus v squared equals u minus v, u plus v. This here is the square of 2ab, and this is clearly a square, so we get 2ab minus a squared plus b squared minus c squared times 2ab plus that thing, a squared plus b squared minus c squared. Now, a little bit of regrouping. Let's first work with this factor. I want to write this as a squared plus 2ab plus b squared minus c squared. The point is, of course, to use that this is a plus b squared. Now, what about the other factor? This one. If I factor out the minus, I can write that this is c squared minus a squared minus 2ab plus b squared. You can check c squared with the plus, a squared with a minus, b squared with a minus, and 2ab with a plus. So, of course, this now is a minus b squared. So I get a plus b squared minus c squared times c squared minus a minus b squared. Again, difference of squares. This here gives me a plus b plus c, or rather a plus b minus c times a plus b plus c. And this here gives me c minus a minus b, c plus a minus b, which I can simplify as c minus a plus b, c plus a minus b. So I get the product of four things. A plus b minus c, a plus b plus c, times c minus a plus b, c plus a minus b. And this is 16s squared. So if I divide this by 16, I can write that s squared equals a plus b minus c over 2 times a plus b plus c over 2 times c minus a plus b over 2 times c plus a minus b over 2. Clearly 2 in the power of 4 is 16, and I immediately recognize that this is p, half the perimeter, and I claim that the other three guys are p minus a, p minus b, or p minus c. Let's check this. What, for instance, is p minus a? That's b plus c minus a. B plus c minus a. This term is p minus a. And it's easy to check that, for instance, p minus b likewise is a plus b plus c over 2 minus b is a plus b plus c minus 2b over 2 is a minus b plus c over 2. It's this term. So this guy here is p minus b. And finally, p minus c equals a plus b plus c over 2 minus c. That's a plus b plus c minus 2c over 2. So this last guy is p minus c. So we get that s squared equals p times p minus a, p minus b, p minus c. So from here, s, of course, is simply the root of this product. So we have proved how many? 1, 2, 3, 4, 5 very useful formulas for the area of the triangle. All were derived from the law of sines and the law of cosines.